Hi, my name is Brandon, and this is my results for experiment 1. So we're going to use tape and determine the charges and forces they exert on each other and the excess atoms from ripping a tape off another piece of tape. So when we rip a tape off another piece of tape, as shown right here at the bottom, we are going to be ripping electrons or protons off the bottom piece of tape, and it's going to give it an excess charge. We're going to treat each tape as a point charge, and we're going to note when things are in equilibrium, they have a net force of 0. Opposite charges attract and the same repel, and yeah. So the results I found is the tape had a charge of 8.44 e minus 9 coulombs, and there were 5.27 e to the 10 excess protons from ripping the tape off the other one. So these are the main equations. When we reach equilibrium, gravity and this force right here are going to be equal to each other. It should be noted that this should be 9e9, not 9e minus 9. So we assume tape is a point charge because it simplifies it. Gravity is only vertical force because every other vertical force is insignificant or they're either horizontal. Atoms are evenly distributed because without this assumption, this is really hard / impossible for me. And we're going to assume the charges on the tapes are equal since they were done the same way at the same time. So you see this what the experiment's going to look like. We're going to put tape B so it hangs and then stick tape A underneath it and it will send tape B up. We'll find this distance D and we'll get the mass of the tapes, and with that we will be able to find all this information. So first we find gravity using the first equation shown. Then we use the electric force equation. We set it equal to gravity since it's at equilibrium, which means these two must be equal. And then we can algebraically manipulate these two to find Q, since QA equals QB, and we get this value of Q. So to find the number of atoms, we know atom has 10 to the minus 10 meters size. So we are going to find the number of atoms in a length. I had a tape of 8 inches long, and then I had a tape of 2 inches wide, find the number in the width, and then we multiply them together, and we get the number of atoms in the whole thing. And there's our ratio of protons to atoms at the bottom. So now we're going to move on to the coding side of things. So first, as you see here, we have our code for the E field. And then we make tape A, tape B, get their gravities. And then we make this new code called Q finder, which is a replica of this, just slightly different to find Q by algebraic manipulation. And from this, we end up with these results, which were shown in the previous slide. Now we're going to move to if we treat it like a line. So these are the results that we get. If you notice, the magnitude of electric force is actually smaller than gravity here. So we get something slightly different. We have the same thing up here. Then we come down. We're going to create the top tape and the bottom tape. And how we're going to make this a line code is we're going to split it into n equals 10 charges with a charge of Q, the last charge we found, over 10. Now, we can find the force of all the charges on each other. Each individual charge on each other charge in the other tape, sum those all together, and we'll get the total charge force, which we saw over here. Now we're going to move on. Get back to this. So assumptions in the point charge was it was a point charge and there were no additional outside forces besides gravity. In the line charge, we assumed there were finitely many line charges that were evenly distributed. There were no interactions between charges on the same piece of tape and no additional forces acting besides gravity. So some possible errors was when we did the experiment, the tape touched my hand, which could have taken away some electrons. My hand could have been attracting the tape down. The tape seemed to be attracted to neutral things too, so it was attracted to the chair. Measurement errors and assumption of point charge could change things a lot, which is actually going to go straight into this question. The difference between point charges and line charges. When we did line charges, we saw that the force of the electrons or the protons was actually less than gravity, which means we needed a greater value of Q than with the point charge. This is probably more accurate since the point charge more likely models real life. And the other thing is what if charges and protons or what if protons and electrons are switched in this experiment? There would be no difference since the same rules would apply, and protons and electrons have the same magnitude of charge. So that's it, and sorry for recording on the phone. I could not get my computer to screen record correctly. Yeah, thank you.